Good afternoon, everyone. So, today is the third week of the lecture Fundamentals of Nano and Quantum Photonics. So, we will just wait for 2 more minutes. If someone joins, then we'll start. Sorry. Okay, so let's start. So, in this week, we talked about the low dimensional materials. So, first of all, I will introduce the low dimensional materials, and in the last 2 weeks we introduced basics of electromagnetic waves, dispersion, and optical properties of materials like metals, dielectrics. So I just want to give overview of electromagnetic waves and material dimensionality. So electromagnetic waves encompass a broad range of phenomena and are fundamental to the characterization of materials. So we will understand their behavior in low dimensional systems, assist in predicting light matter interaction at the nanoscale. So, what is the importance of dimensionality in materials? So, material dimensionality significantly influences the electronic and optical properties. So, when there will be a transition from bulk to low dimensional configuration, it will alter confinement effects and modifies the fundamental processes such as absorption and emission. So, if we talk about in bulk material, so in bulk material, when we're talking about 3D, so let's suppose there's a cubic lattice. So it's a 3D systems where electrons are confined, where electrons can move freely in all the three dimensions in X, Y, and Z. So electron in this cubic lattice, electrons can move freely in all the three dimensions, and if we confine the electron to move only a certain plane, so If we confine the electron to move only in a certain plane, then we say 2D. So 2D. That is the example for this quantum well. And so light is allowed to travel only in one plane. So suppose this is y, this is g, this direction is x. So now light is confined in x only but can freely move in y and z direction. And if we consider nanowire, nanowire, so light is confined only along x and y direction. Suppose this is your z direction. So light can freely move in z direction only and confined in an x and y plane. So then we will say it 1D material. So we here we define, and if the light is confined in all the three direction, then it will be a quantum dot. So in quantum wells, wires and dots represent various low dimensional structures that confine electrons in 1, 2 and 3 directions respectively. Their unique proper their unique geometries led to distinct physical properties and potential application in nanotechnology. So let's understand low dimensional system. So how can we define the low dimensional structures and their comparison with bulk materials? So we will learn that how the optical properties change with size. So low dimensional systems are characterized by their reduced dimensionality, where electrons are confined in one or more spatial dimensions, leading to enhanced quantum effects that are not present in bulk materials. So, unlike bulk materials, where carriers can move freely in three dimensions, so since with low dimensionality there will be quantum confinement, resulting in the phenomena such as quantized energy levels and the modified optical responses. So we saw that in the previous lectures when we were talking about the energy band. So for bulk material, energy levels are continuous. We saw that energy levels like this is is forming a proper band. Okay. So now when the dimensionality will reduce, the energy levels will be like this. So the energy levels will be quantized. So now we can see the discrete levels. So like quantum wells are thin layers with confined electrons in two dimensions, while nanowires provide one dimensional confinement. Quantum dots are zero dimension nanoparticles with discrete energy state then that enhance photonic characteristics. So since we defined metals by Drude model, so it was epsilon omega is equals to epsilon infinity minus. So this equation was for bulk matter. So for metals, we need to worry about the change in optical properties when we are going below the size of 2 or 3 nanometer. So confinement effects is it's an important property on the basis of which we will solve one or two problems. So confinement effects will be significant below the size of 2 or 3 nanometer. Greater than 3 nanometer, we will not talk about the confinement effects. So now, so earlier this formula for bulk metal has only the dependency of omega. Now this will have the dependency of k also, wave vector, k and omega, where k is, what is k? So k is equals to 2 pi by d. So that d represents the size of the particle or thickness of the cell. And we this is special frequency. So we can see how for bulk metal the formula is different. There is no dependency on our wave vector, no dependency on special frequency component. But here, when we are considering the size below than 3 nanometer, automatically the dependency of K will come in the permittivity. So we can say that for semiconductors, these effects are significant. So we saw, like we explored the Drude model and dimensional effects. So what was Drude model? So the Drude model described the electrical and optical response of matters through free electron behavior, providing the foundational insight into how these electrons interact with electromagnetic fields when confined, and what is the impact of dimensional confinement on optical properties. So as the dimensions are reduced, we saw that there will be dependency on special frequency, and the electron behavior in matters will diverge from classical predictions, leading to alterations in absorption. So that, or reflectance or conductivity, so that will eventually that will affect their optical response. So what are the thresholds for significant confinement effects? So at certain dimensional thresholds, typically on the order of nanometers, significant changes in optical properties arise, and revealing the profound effects of quantum confinement, and that can enhance or diminish the optical responses. So, so we know that for semiconductors, for semiconductors, these confinement effects are significant. So why is this so? So we can put a question that why low dimensional systems important? my low dimensional systems. So used in LED devices, lasers. So we want to integrate some device with the chip, then it should be order of that smaller size. And if we are decreasing the size of the device, then obviously quantum effects will be prominent. And where we cannot use, so lasers, we want to make micro nano lasers in micro and nano dimension, so which will be central to the optical or communication system. So we are talking about nanophotonics, means nanoscale phenomena. So earlier when we talk about bulk material, there was valence band and conduction band. Now this, so 1s, 1p, 1d. So these are for holes, and these are for similarly for electrons. I can consider this for quantum pairs or quantum well, or levels are discrete. So we can see that energy levels are no longer continuous. We have discrete energy levels. What does it mean? So where we can use this quantum dots. So we have discrete energy levels. So we can have the emission at different wavelength. So here that Eg is equals to Eg bulk plus delta E, and that the difference. So what are the applications of low dimensional system? Technological relevance in various fields. So low dimensional systems are essential in the development of advanced light emission technologies, contributing to the efficiency and performance of sources like LEDs and lasers. Since if there are discrete energy levels, means emission at different wavelengths. So you can see that lambda. So for quantum dots, there will be sharpness. So for this wavelength, for this wavelength, for this wavelength, we can have emission at different wavelengths. And if we are using if we are using these materials in LEDs or laser diodes, then it can significantly enhance their efficiency and spectral performance while reducing the at the same time they will reduce the energy consumption and the cost also. So what is the impact of these low dimensional materials on telecommunication and nanophotonics? The unique optical properties of low dimensional structures have profound implications for telecommunication and nanophotonic devices, facilitating advanced signal processing and miniaturization. So the spacing, one important note is that the spacing between the energy levels are dictated by the size of the particle. Okay. So next we will talk about absorption in semiconductors. So for direct, so what is the mechanistic insight into how materials interact with light? So what is the mechanism of absorption? So absorption occurs when photons interact with electrons in a material, promoting them from a lower energy state to higher energy state. This process is fundamentally tied to the material's electronic structure and is quantified by the absorption coefficient, which determines how deeply light can penetrate before being absorbed. So that we know. We have already talked in the previous lectures that alpha is our absorption coefficient. So valence and conduction band. So the distinction between valence and conduction band is crucial. In solid state physics, electrons in the valence bands can be excited to the conduction band upon absorption of sufficient energy, that we have already seen that the band gap or the energy difference between these two bands plays a vital role in determining a material's optical absorption characteristics. So if the energy of the photon is lesser than the band gap, then it will not interact with the material, it will just transmit. But if the energy of the photon is greater than the band gap of the material, then it will interact with the material and that photon will be absorbed by the electron. So now this is the threshold behavior and the band gap. So the band gap EG. So this band gap will determine the threshold energy necessary for the electronics transition. So materials with smaller band gap exhibit significant absorption and lower energy photons, while those with larger band gaps typically requires higher energy photons for absorption, which is critical for designing materials for specific optical applications. So, we saw direct band gap in which the peak of the valence band and the bottom of the conduction band lies at the same K. Then this is direct band gap, and these are the important. So direct band gap means you need the energy equals to the band gap only. This much energy is enough to do transition from valence band to conduction band, and then the photon will emit when the electron from the conduction band will de-excite to the valence band. So for the photonic direct band gap, semiconductors plays an important role. So for examples like gallium arsenide, gallium phosphide, and then there is indirect band gap semiconductors where this peak of the valence band and the bottom of the conduction bands doesn't lie at the same cave at the same wave vector, so that you need much more energy to do the transition from valence band to conduction band. So then phonon comes into picture in case of indirect band gap. So example, silicon and germanium. So you can see that for indirect, so what is the cause of this? So in indirect band gap semiconductors, so there is a mismatch in momentum. And if there is a mismatch in momentum, that's why silicon and germanium are not very good at absorbing photons. So absorption process depends on two rules. One is conservation of energy, and the other one is conservation of momentum. So conservation of energy means energy in the final state minus energy in the initial state is equivalent to the energy of the photon. And when we'll talk about conservation of momentum, then h cross k, that is the photon momentum is equals to H cross V vector in final state and the V vector in the initial state. So conservation of momentum is not satisfied in indirect bandgap materials. So that's why these are not good at optical absorption as compared to the direct bandgap semiconductors. So now we will define the concept of optical gain. So how can we define the optical gain and its relation to absorption? So what is the definition of optical gain? So optical gain refers to the increase in the intensity of light as it passes through a material. So we saw that initially we were talking about alpha. So when the light was passing through a material, the amplitude was decreasing. So it's again. So now when we are talking about gain, means the amplitude is getting amplified. So this process is primarily due to stimulated emission, and this process amplifies the light instead of merely absorbing it, making it essential for the operation of lasers and optical amplifiers. So we can do comparison with absorption. So that while absorption reduces the energy intensity as it traverses a material, optical gain enhances it. So the interplay between absorption and gain defines a material's efficacy in light emitting application and is dynamic depending on external pumping conditions and electron density. So, what are the conditions for achieving gain? So, just if we talk about lasers, there must be population inversion, right? So, to achieve the optical gain, certain conditions such as population inversion must be met. This occurs when a greater number of electrons exist in an excited state, necessitating specific excitation methods and environmental control to successfully harness this phenomenon. So, how can we define the absorption in semiconductor for the bulk material? So, absorption in semiconductors are essentially given by the Fermi's golden rule. Fermi's golden rule. So, what is this? So, it is represented by W, the transition probability, that is defined by 2 pi by h cross wave function in final state, your perturbed Hamiltonian. So this whole is this we have matrix element, and then G H cross omega. So G H cross omega is density of states. So how can we define the how will we solve the matrix element? So M is equals to F your per-term Hamiltonian is equals to integration your wave function in final state, wave function of electron in final state as a function of R, perturbation, perturbed Hamiltonian, and then initial wave function of electron greater than R. So if we define H prime, so if there is a dipole moment and it is interacting with the electric field, then our perturbed Hamiltonian will be minus P dot E, that is X E inert iota kx. So if someone asks that are the should we consider the confinement effects if the electrons are moving inside a lattice or atom? So yes, because it is of the angstrom unit, so lesser than the 2 nanometers and 3 nanometers. So we have to consider the confinement effects. So if we consider the electron in a crystal, electron in a crystal, that is psi AUX E iota. So that UX is, since the potential is periodic, so we have to consider the block function. So here this UX is the block function that will represent the periodicity of the potential. So this is block function represents the periodicity. Now if we consider this M is equals to U star X E iota kx. So if we will take conjugate of this, so iota will be minus iota u dash x e minus iota kfx, then x h, we will substitute the value of h perturbed Hamiltonian, and then psi e iota kix. So this is for the unit cell. So total. So now here assumption is that one assumption is that each unit cell is giving a same phase. So the total is E iota caps K minus kf minus kix. So if k is equals to k is not equals to kf minus ki, each unit cell will give us a different phase. So this is one important thing. If and also if kf minus ki is equals to 0, that is, so suppose this is 0, then m, our matrix element, will be non-zero. So what does this imply? So if this value is non-zero, it implies there is some absorption. So now we will talk about, so we saw that if that matrix element is not is non-zero, then it has some absorption. And so we can define this g omega, that was the density of states. So the number of states between e and e plus delta e. Similarly, number of states between k and k plus delta k. So GEDE is equals to GK dk. So now, what are the processes that leads to the light emission in materials? So there are various transitions. There is radiative versus non-radiative transitions. So radiative transitions occurs when an electron drop from a higher energy state to a lower energy state, emitting a photon, while non-radiative transition results in energy release as thermal energy rather than photon. So these processes are, so to understand these processes are essential for optimizing our light emitting devices. So then we will talk about what is the role of electron hole combination recombination. So what is electron hole recombination? So electron hole pair, if we have the electron hole pair and that are bounded by some Coulombic interaction, is known as exciton. So what does this name refers to? Exciton. So exciton means excited electron. So electron and hole pair, when they are, so electron has moved to the higher energy state, but still that electron is bounded by the hole present in the valence band. So by the Coulombic interaction, so we say that exciton. So one important note I want to discuss here, that is, so excitonic binding energies are small for bulk materials at room temperature. So that's why we go for low temperature, since if the temperature, so at room temperature, if the binding energy will be less, then the electron and hole will no longer be bounded, and we can't find the exciton. So that's why we go for low temperatures. for 2D materials like TMDCs. At low temperature, we get a strong exciton absorption. So strong absorption excitonic peaks. What does this imply? Strong absorption excitonic peaks means absorption is stronger. So electron hole pairs in semiconductors can recombine to emit light. This process can be either radiative or non-radiative. For effective light emission, maximizing radiative recombination is crucial as it contributes directly to the device output efficiency. So different materials exhibit distinct emission characteristics based on their band structure and transition mechanisms. So for example, like third and fifth group like gallium arsenide, third fifth semiconductors are renowned for their efficient light emission, while organic metals materials offer unique capabilities in flexible electronics and photonics. So here, so next we will talk about the quasi Fermi levels and the non-equilibrium conditions. So we will understand the impact of external pumping on material states. So what are quasi Fermi levels? So quasi Fermi levels represents the effective energy levels for electrons and holes separately in non-equilibrium condition, and this is useful for understanding how optical gain can occur in semiconductors by separating the populations of charge carriers after excitation. So if we have here valence band, conduction band, topped with n-type semiconductors. So here we will have Fermi level. So impact of pumping on electron density. Pumping alters the electron density in a material, leading to separation of quasi-Fermi levels that signify altered Fourier distribution. This change is essential to achieve desired gain conditions in optical devices, facilitating stimulated emission and excessive absorption. So, what are equilibrium versus non-equilibrium scenarios? So, in equilibrium, the distribution of carriers is stable and follows the Fermi-Dirac statistics. Non-equilibrium scenarios influenced by external excitations create gaps between the quasi-Fermi levels, establishing establishing conditions for optical gain. So understanding these states is vital for device engineering. So how can so we will understand now, like if you want to confine an electron, then what are the necessary conditions? So suppose if we want to confine electron in a dimension which is delta x. So what according to Heisenberg uncertainty principle, delta p is equals to H cross by delta X. So what will be my confinement energy? E confinement is equals to P square by 2m, which is H cross square by 2m delta X square. So now our confinement effects will be significant when my confinement energy, that is H cross square by 2m delta X square, will be greater than my thermal energy, that is given by the KBT. K is B is Boltzmann constant and the T is the given temperature. Sorry. So when this condition can be achieved? So this condition can be achieved when this can happen. It can happen when delta X is very very small. So by using this formula, we can find the thickness of semiconductor. When will confinement effect will be prominent? So we can find delta X is H cross 2m E. So we have defined that kBT is equals to AT, our thermal energy. So basically, if this is a condition, if your the semiconductor thick if the thickness of the semiconductor following is in this range, then we have to consider the confinement effect, and then, or we can say, delta X is less than d Broglie wavelength. So if I consider that, like if M effective is equals to 0.21 ME, then what will be my delta X? It will come around 5 nanometer. So from this what we can say, if we confine an electron to a dimension of 5 nanometers, so we will see the confinement effects. So we have to consider the quantum behavior of the electrons. So for low temperature measurements, one important note here, for low temperature, so if we are dealing with the low temperature measurements like for TMDCs, where we want to see the exciton, like either dark exciton, bright exciton. So for low temperature, what will happen? At low temperature, our energy will reduce, energy decreases, and this delta X increases. So what is the benefit So, and why do we go for low temperature measurements? Since we saw that if the energy will reduce and delta X will increase, so the confinement effect will be visible for the large thickness also, say at 25 nanometer, which is 5 times of 5 nanometer, which is at room temperature. So at room temperature, if the thickness of semiconductor will be 5 nanometer, then only we will be able to see the confinement effect. And if we are doing the low temperature measurement, then we can see the same confinement effect for the 25 nanometer thick semiconductor, for the thick semiconductor. Okay. So what is the role of this optical gain in devices? So what is the real world implementation? So this concept of optical gain is foundational to the function of lasers and LEDs. So in lasers and in lasers, gain medium are engineered to maximize the stimulated emission, efficiently move converting electrical or optical input into coherent light, while LEDs utilize similar principles for solid state lighting. So what is importance in telecommunications? Optical gain plays a crucial role in optical fiber communication with amplifiers based on gain necessary for long distance signal transmission, and the ability to maintain signal integrity over vast distance relies on effective gain mechanism within materials. So what are the future trends in optoelectronics materials? The evolution of materials with tailored optical gain properties is paving the way for innovation in various sectors, including energy harvesting, data transmission, and advanced display technologies. And our ongoing research is focused on enhancing performance and finding new applications for optical gain. So we just talk about like what is the Heisenberg uncertainty principle and confinement energy. So the Heisenberg uncertainty principle highlight the intrinsic limits in simultaneously knowing a particle's position and momentum, critical to understanding the quantum confinement. And also we did the confinement energy formulation, like confinement energy derived from the uncertainty principle, correlating the dimensions of the quantum systems to energy levels. And what are the conditions for confinement effects? So we saw that significant quantum confinement effects are typically observed in materials with dimensions smaller than the exciton Bohr radius. We saw that for an electron in the crystal, it is lesser than 5 nanometer at room temperature, and the same effect is visible at 25 nanometer if we are dealing with the low temperature measurements. So now here we will talk about the density of states in quantum structures. So we will basically quantifying the electronic states. So the density of state describe how many electronic states are available. So number of states between E and E plus T. Number of electronic states are available for occupation as a function of energy. So varying significantly between dimensions. So next, or we can say number of states between K and K plus Tk. So we can define GE DE is equals to GK DK. GE is equals to dE. So if for a 2D material, so for a material we are defining gk is equals to k square by 2 pi square g is equals to 2 gk d by dk. From this we can also define E is equals to h cross square k square by 2m GE is equals to C under T. So we can see that absorption is proportional to E minus EC when H nu is greater than EG and 0 when H nu is lesser than EG. So here this is photon energy and this is alpha, that is absorption coefficient. So optical quantum effects, confinements alters. So when we will consider the confinement effects, it will alter the density of states, leading to an increased number of available states at certain energy levels. So that will fundamentally modify the optical transition. So now when there will be a change in the density of state due to quantum confinement, it will change the probabilities and the mechanisms for optical transitions within the semiconductor nanostructures. So we saw that how will the energy is changing. It is showing the parabolic behavior. So absorption generally shows parabolic behavior, but it deviates because of excitonic effects. So in general, En is equals to Eg minus Rx by n squared, where Rx is Rydberg constant. Okay, let's take 10 minutes break, then we will continue revision and we will do the assignment. Okay, let's continue. So, we were talking about the optical response. So, we studied that optical the transition is explained by the Fermi. The absorption in semiconductors is defined by the Fermi golden rule. Omega initial transition probability from initial state to final state is given by 2 pi by h cut, then matrix element, and then the density of states. So here we are considering one example, that is particle in a box. So for particle in a box, the wave function, let it be psi of x is equals to sine of n pi x by l, where n is equals to 1, 2, 3. So you can see that for n is equals to 1. So the width of the quantum well is, so the width of the quantum well is L, and we will write the matrix element psi I AV UV, like just like we defined for the block function AV UV E iota k dot r, and we are assuming that phi n is a wave function. Then for the psi f, similarly in the conduction band, and then we are simply defining m is equals to MVC transition and m and n prime. So n prime will be will be equals to integration of phi n as a function of z, phi n dash as a function of z and dz, since it represents the electron hole overlap integral, and the MVC represents the valence band conduction band dipole moment. So the final wave function. So So we saw that the energy of this, where Kn is equals to n pi by L, and the energy will be defined by h cross square n square h cross square pi square to L square. L is the length of the quantum, width of the quantum net. So here, like uh, you can see this wave function is for E1. So you will substitute n is equals to 1, and you will have h square pi square by 2 lambda square. Similarly, if you want to find out E2, it will be just a 4 cross h cross square, that is equivalent to 4E1. So when you will plot the sine 2 pi x by L, these are the wave function, even function, odd function for different levels. Then what are the selection rules? So absorption is a quantum well is strong excitonic absorption in visible. So from this figure you can see that if the delta so you were talking about the selection rule. So selection rule means like whether the transitions are allowed or forbidden. So for that we will see the product of matrix elements. So we saw that we studied the two essential laws of for the energy, which was conservation of energy, conservation of momentum, and the third will be decided by this matrix element. So on the basis of that, if it will be non-zero, then only if that k is equals to kf, then only the absorption will happen. So now, So for the bulk semiconductor, A is given by absorption is given by H cross omega minus Ag 1 by 2. Here no exciton. In bulk, no exciton. Then quantum width, band gap is shifted. How much? Eg QW is equals to Eg bulk plus what is the n square h cross square pi square by 2 mm square. So, so for the quantum well, what are the main characteristics that is happening in the case of quantum well? First of all, band gap gets shifted. Second, this is first thing. The second thing is exhibit step-like behavior. Third thing is splitting of exciton peaks. How the exciton peaks will split? Depending on heavy holes, light holes. Heavy holes, electron or light hole electron. So, so in that case also if delta n, so when we will solve this whether absorption can take place or not. So if the delta n is equals to even, then it means forbidden. If the delta n is equals to odd, it is allowed. So in this case, you can see that there is psi 1 represented in blue part, psi 2 is represented by red part, and then this black part is represented the combination of this both. This integral is represented by the pink part. So you can see if the delta n is equals to 1, then it is equally. So all the integral is positive. So psi is not equals to that matrix element is not equals to 0, that it means the transition is allowed. So but when delta n is even, then you can see that this pink line positive part is cancelled by negative part, so that transition is forbidden. So that transition can not take place. So from here we can see that if we are, what is the transition strength, where will be the greater absorption if I am if I am that if the transition is from first level to second level, or first level to fourth. So you can say if it is moving from 1 to 2, the integral is 0.55. But if the energy is 0.55, if the transition between from ground state to third excited state, then the energy is 0.04. So you can clearly see the energy from ground level to second level is 12 times stronger than the transition from ground level to third excited state. This is one thing. The other thing is, so the energy formula is n is equals to pi square h square upon 2m L square. So this L is width of the quantum well. So if the width of the quantum well or potential well increases, this matrix elements becomes bigger and the absorption will be stronger. So L If L increases, alpha increases. So this was all about the lecture. Like this was all about the optical response in bulk materials, optical response in quantum wells, and we dealt with the dimensionality of the materials. We saw the absorption in the semiconductors is given by the Fermi's golden rule. So on the basis of whatever we studied today or whatever we studied in this week, we have some problems regarding that. That is assignment 3. So we can solve the assignment now. So the first question is quantum confined semiconductors are artificial structures in which the electrons and holes are confined in one or more direction. Consider a nanowire 1D system of diameter 50 nanometers and length 10 nanometers. The length of the nanowire is along z direction. Choose the correct statement regarding the electron confinement in the nanowire. So it is given that nanowire. So we know that it's given is 1D system. So in the question they have mentioned that the length of nanowire is along the z direction. So if this is given the z direction, so we saw and we from the option like we can clearly say that electrons can freely move in z direction and confined in x and y direction. So first option is electrons are confined in z direction and are free to propagate in the xy plane. This is completely wrong because we know that electrons can free in 1D system. Electrons can move freely in one direction only. Second option is electrons are confined in xy direction, free to propagate in the z direction only. So this is correct option. What are the other options? Electrons are free to move around in x three direction is not possible. Only in the x direction and confined in the y direction. So since they have mentioned that the length of the nanowire is along the z direction, then only we can say that okay, in the z direction electrons can move. So the right answer is second option. Second question is for a typical semiconductor at room temperature, the approximate size of the structure below which quantum effect are significant is approximately. So theoretically, we can tell obviously, like we saw that for the electron, where the quantum effect, even we during revision we consider also this example, me star is equals to zero point 0.1. I'm not. Okay, so for that we found out that it was coming 5 nanometer we have given. So with the given parameters also we can solve it. So suppose we have 1D box and the quantum confinement energy is equals to, we are considering ground state, 2m star L square. And since this is equivalent to, if we equate it with thermal energy, Then we can find out L square. So from this we get, after putting all these values, we get L is equals to zero point 0.4 nanometer. But we saw that, so quantum confinement is significant theoretically when the structure is size is lesser than 10 nanometers. So 5 nanometers is a better choice. So for the 5 nanometers, the quantum confinement effects will be significant. This is a very interesting question. The figure below gives absorption data for gallium phosphide at 300 Kelvin. Answer the questions based on the given data. So we are given the alpha square versus energy plot, and alpha. So first of all, graph is between alpha square and energy, not alpha and EV, the first main point. So we saw that for direct band gap semiconductors, absorption coefficient is proportional to, and we saw that it shows the parabolic behavior. So for the alpha square, it will be proportional to h nu minus Ez. So if we will plot between alpha square versus h nu, this plot should give straight line, right? But this was for direct band gap semiconductor. Then near the absorption edge. Okay, so since we can see that it's not a straight line, hence we can, so the question is gallium phosphide is a direct semiconductor, indirect semiconductor, or it cannot be determined by this graph. So we can clearly see that, like, it is a plot between alpha square and it versus energy, and it should be a straight line for direct band gap semiconductors, but it's not a straight line, so it's an indirect band gap semiconductor. Okay, so next question, the approximate band gap of gallium phosphide is, so obviously we saw that it is how is going next 0 0 then this, so here it was 2.7 electron volt approximately. So below 2.6 electron volt alpha square was 0, and after starts increasing. So the right answer is the approximate band gap of the gallium phosphide is 2.7 electron volt. Okay, so next question is, given below are two statements regarding the quantization of energy levels in a quantum well with infinite potential barriers. So the first statement is the quantization of energy is same for electrons, heavy holes and light holes. And the second is the energy of the levels depends on effective mass of the particles. just we saw that what is our quantum confinement energy? N square I square h cross square upon 2 effective mass m star L square. So obviously the energy depends on the effective mass of the particle. So now we know that statement 2 is correct. Okay. So statement 2 is this is true. So if the statement 2 is correct, then what is the statement 1? The quantization energy is same. If it depends on the effective mass of the particle, and we know that the effective mass will be different for electrons, will be different for heavy holes and the light holes since it has different masses. So obviously our quantum confinement energy will also be different. So the statement S1 is false. So now statement the correct answer is B option. The statement S1 is false and the statement S2 is true. The next question is consider an infinite one-dimensional potential well of thickness L is equals to 10 nanometer. The effective mass of electron in the potential well is m star is equals to 0.1 m naught at room temperature. So we want to find out the energies of the first and second levels are. Okay. So we are given that L is equals to 10 nanometer, m star is equals to 0.1 m naught, T is equals to 300 Kelvin. So E1 is equals to pi square h cross square to m l square. So we will substitute h cross is equals to 1.055 into 10 raised to power minus 34 joule second. So our E1 will come 37.6 milli electron volt, which is 37 milli electron volt. So what will be E2 is equals to 4 pi square h square 2 ml square 4 E1. 37 is equals to 148 millielectrons. So this option third is correct. So consider the following statement. The quantum description for the motion of electrons is essential for the given potential well. And the statement second is the quantization energy is higher than the thermal energy at the room temperature. So in this question, we are dealing with the L is equals to 10 nanometer. Okay. So if we are dealing with the 10 nanometer, it means it is wide quantum well. So the energy levels are quantized. Okay, we saw in the previous question. Okay, the energy levels are quantized. So energies are discrete. Classical physics cannot explain this behavior. Quantum mechanical treatment is essential. This means S1 is true for the given length. Okay, so we have to treat it as a quantum description of motion for the motion of electrons. Okay, then the second is, so we calculate that E1 is equals to 37 millielectron volt and kBT, that is our thermal energy, is equals to 25.9 millielectron volt. Clearly we can say that E1 is equals to kBT. So if the E1 is greater than kBt, so what is the important thing that thermal motion cannot smear out the energy levels, electrons, so it will make quantum treatment necessary. So the correct option is S1 is statement S1 and S2 is true, and S2 is the correct explanation for S1. So the next question is semiconductor devices of various dimensions are given on the left side of the table. Match the system with their corresponding density of states, energy dependence on energy on the right. So we saw that for a 3D system, rho of epsilon, rho of directly proportional to E1 by 2. So density of states is proportional 1 by 2 for 2D E is equals to E naught, that is constant. 1D E proportion to e to the power minus 1 by 2. In zero dimensional, it will be a delta function, the Dirac delta function. So it will represent the discrete energy levels. There is a short formula for this also, that E n by 2 minus 1. So for 3D 3 by 2, put n is equals to 3, where n is so n is equals to 3 is proportional to e and 3 by 2 minus 1 by 2. If you will put n is equals to 2, 2 by 2 minus 1, 0, so it will be constant. 1D के लिए 1 by 2 minus 1 by 2, and for 0 के लिए it is discrete levels. So the correct answer is for 2D. So A will be 3, B will be 2, C will be 4, A3, B2, C1, and D4. So this is the correct answer. Next is the figure below. This depicts an infinite quantum well with electron wave function for 5 different energy levels. The transition from lower to higher energy levels for 3 different absorption processes are marked with A, B, and C. So based on the selection rules, the allowed transitions are. So here we are given. So we know the wave function size for 1D box root 2 by L, and How should we choose psi m and psi nx? The transition will be allowed if this will be non-zero. So let's see the first transition A. So A is transition from E1 to E3. So E1 to E3 delta n is equals to 2. That is E1. That is forbidden. So 1 3. So if you substitute m is equals to 1, n is equals to 3, then this product will be even function, and but x is there, so x is multiplied, it will make the odd function, so that will be become, this integral will become 0. So that's why it is forbidden. So P is the transition from E3 to E4. So delta n is equals to 1. So then this transition is allowed. C is E3 to E5. Again, delta n is equals to 2. It is forbidden. So what are the options? Only A, B and C, A and C, only B, only C. So we saw that only the transition B is allowed. So the option C is correct. And the next question is the exciton energy for the nth, the exciton energy for the nth level related to ionization energy is given by Eg minus band gap. We derive this relation. We know that semiconductors shows, so it is, we saw in theory also, En is equals to Eg minus Rx by n square. Rate constant and n is principal quantum number. And the last question of this assignment is the wavelength of the absorption ends of a 20 nanometer gallium arsenide quantum well for n equals to 1 compared to gallium arsenide at 300 Kelvin is. So we are given the values, that is, one important hint is given here that absorption edge for quantum well is the band gap plus the quantization energy of holes and electron. So Eg, what are the given? Eg gallium arsenide is equals to 1.42 electron volt. E electron for n is equals to 1, 14 milli electron volt. E H plus is equals to 2 milli electron volt. So what we know? Absorption. Use that formula. Absorption edge for quantum well is the E quantum well is equals to band gap plus quantization energy of electron plus quantization energy of hole. So the total energy, what is the band gap? 1.42 plus 0.014 plus 0.002. So what is the total energy is 1.436 electron volt. So this is for when we are considering quantum well, when the energy is in the quantum well. So For bulk, gallium arsenide is equals to lambda bulk is equals to 1240 by 1.42 electron. This given that for the bulk is, so it will give you 873.2 nanometer. And for quantum well, 1240 by 1.436. It is 863.99 nanometers. So you can see that for bulk is it 873. For quantum well it is 863.9 nanometer. So it is almost shifted by 10 nanometer compared to bulk gallium arsenide. So now the question comes, blue shift or red shift? So for bulk gallium arsenide, the lambda is 873, and for the quantum the lambda is 863. So the lambda is decreased. So if the wavelength is decreasing, then it means it is blue shift. So the first option is red shifted by 10 nanometer is wrong. Then blue shifted by 10 nanometer compared to bulk. This is correct. Shifted by 30 nanometer. So the option B is correct. So this was all about the assignment. So in this lecture we solved assignment 3, and we have revised the what is the optical response in the bulk materials as well as the quantum wells, quantum dots. We deal with the dimensionality of the materials and how the materials show the absorption in different dimensionality materials. So this was all about today. So thank you.